In this video, we are going to understand the transformer in just 7 minutes. We will cover the concept of the multi-head self-attention here and the positional encoding here. When looking at the transformer architecture, it's an encoder on the left side and a decoder on the right side. You may be confused why in the decoder, the multi-head self-attention is called the masked multi-head self-attention. It is because during language generation tasks, the model should only use previous and current tokens to predict the next one, so the mask is here to block future position in the decoder. Here is a picture of multi-head self-attention, which is also called the MHSA in brief. And the concept of MHSA is not only well used in natural language processing, large language models like ChatGPT, but also widely adopted in computer vision, like vision transformer. So we will explain the multi-head self-attention firstly. Here is a picture of the multi-head self-attention, where the Q is a query, the K is a key, the V is a value. What's the meaning of the value, key, and query? So let's explain it. Let's give in an example sentence. Exploration is fun. So in this sentence, we have 4 different words. And if we can use text embedding to embed this sentence into different vectors for each position, where the exploration would have a vector, is would have a vector also for this and this. And if the embedding size is 512, then the sentence would be converted into a matrix like this. So the 4 represents for the sequence length, and the 512 represents for the feature number or the embedding size, or we can say the number of channels. And if you use the multi-head self-attention during the training stage, the input data would shape like this. The base size in dimension 0, the sequence length in dimension 1, and the demodel in dimension 2, where the demodel is just the embedding size. Then after embedding, our input data can be input into the multi-head self-attention. We copy the input sequence 3 times, and we get 3 input sequence here. They are totally the same. And each of them will multiply by weight matrix from the model. They are learnable weights. And we get the QKV matrix after the multiplication operations. So here, after the linear function, we have Q, we have K, and we have the V. And before the operations, the QQV is just the input sequence where X, and also X. And after this, these linear layers, they will change into the QKV. And later, the scaled dot product attention will be applied. Now, here is the formula of self-attention in transformer. And looking at this formula, we can see this thing on the left side and the value matrix on the right side. The scaled dot product operation is applied here. So what's the meaning of this operation here? Remember, we have a sentence called exploration is fun, and we let each word be a query here. So the exploration is a query, and we let each query multiplies by all of the other queries in the sentence. So let's say exploration multiplies by 8, exploration multiplies by fun, also multiplies by itself and for this. So the product of the query matrix for each word and the key matrix for all words in the entire sequence, this can represent the attention score for each position and the rest of the other positions. When we write it in the format of a matrix, It is just the Q matrix multiplied by the transposition of the K matrix here. And we also divided it by the decay. The decay is the number of features we have. We apply a softmax here, and so that after this operation, we get a matrix here. And the softmax can just map each value in the matrix into a value between 0 and 1. So let's say 0.1, 0.2, 0.11. So we got a matrix like this, and this matrix can be seen as an attention score matrix. So later, we use this matrix multiplied by our value matrix to get the final output weighted by the attention score. So here, the self-attention is achieved. In this picture, we only show one of the channels in the entire feature number. So remember that we have 512 features. And if we have 4 attention heads, so each attention head is responsible for the number of 512 divided by 4 channels, and then the output of each attention head is concatenated, and we use a WO to map the dimension of the matrix into the same dimension of the output from each head, so that we don't have too many channels of features. Next, we are going to understand positional encoding. In the original transformer, the positional encoding is called sinusoidal positional encoding. Before we introduce it, we should know 2 goals that we want to achieve. The first is we want each position to have a unique vector. For example, if we have a sentence called ABA, and if we don't use a positional encoding, then the vector of A of the 2 different positions is totally the same in the very beginning, right? After we use positional encoding, the vector of this A and the vector of this A will be different. Second, the sinusoidal positional encoding can let different dimensions to focus on different scales of position difference. Here is a formula of the sinusoidal positional encoding. We have the discriminator here that represents for the frequency. That means how fast a wave oscillates. The pulse here represents for the position of the token. The I represents for the order of the current channel. We have 512 channels, and after the positional encoding, the output of it will be directly added with the original matrix. When looking at this formula, for small I, the discriminator here is close to 1, so it can capture some short-range patterns. And oppositely, for the large I, then the discriminator will become very large, and this can help us to capture some long-range patterns of the position. And when we do the multiplication operation between the Q matrix and the transposition of the K, then the product between the 2 position-aware embeddings will reflect how far apart they are, so because of the sine and cosine waves shifted across the position. And our transformer model can have the ability to capture this positional feature so that it can achieve a better performance.